Section 10.3 is about the properties of logarithms. Since logarithms are just the opposite of exponents, there are properties of logarithms just like there are properties of exponents. The first one we're going to look at is called the product property of logarithms. And that says that if you have a log with a base and you're multiplying two things, so the log of a product, you can split that up by adding the log of the first value plus the log of the second value. Notice the bases have to be the same, but then you're going to add those two logs together. So if I do log base 3 of 4 times 7, that's log base 3 of 4 plus log base 3 of 7. An example of using that can be seen here. If I know log base 2 of 3 approximate to this number, how can I find log base 2 of 48? Well, because I know log base 2 of 3 is something, if I can get a 3 out of this, that would be helpful. And also because I know that log base 2 of 2 will cancel, I can look out for that as well. So I'm going to take log base 2. I know that 16 times 3 is 48. So I could do 16 times 3 here. And 16 is just 2 to the 4th. So I could make log base 2 of 2 to the 4th plus log base 2 of 3. Now I know what log base 2 of 3 is, but when you have a log with a base and you have a base with an exponent that matches the base of the log, those will cancel because this is an exponential function and this is a log function and those are opposites of each other. So those will cancel, leaving me a 4. And 4 plus log base 2 of 3. Well, we know what 4 is and we know what log base 2 of 3 is. So this is going to be 4 plus 1.585. So we can say that log base 2 of 48 has an approximate value of 5.1585. Here we're going to look at the quotient property for logarithms, and that says if you're taking the log of a quotient, you can break that up into two separate logs that are being subtracted. So in this example, I want to find out what the log base 3 of 4 is. Well, I know what the log base 3 of 5 is, and I know the log base 3 of 20. Well, can I write 4 as 20 over 5? So I could rewrite this, as 20 over 5, because that equals 4. And now I can use my quotient property of logs, because I'm going to rewrite this as log base 3 of 20 minus log base 3 of 5. And that's straight from the quotient property. I know that log base 3 of 20 is about 2.7268. And I know that log base 3 of 5 is about 1.465. So I'll take a calculator and subtract those. And I'll get about 1.2618. And so that is what the log base 3 of 4 is approximately equal to. Now, one thing you could do to verify that this is correct is you could use the definition of logarithms and say base 3 to the 1.2618 power should equal 4. And you could type that into a calculator. If you plug 3 to the 1.2618 power, you're going to get probably 3.999, which is very, very close to 4. And so that's one way that you can check your answer by using the definition of logarithms. Our next property is the power property of logarithms, and that says if you have a value to a power, you can take that exponent and move it in front of the log. So notice the p here was in the exponent, so we moved it in front of the log and then multiplied it. We'll illustrate that by looking at an example. I want to find log base 4 of 36. I know what log base 4 of 6 is, so if I can rewrite this with a 6, so I could say log base 4 of 6 squared. And now the power property says I can take that 2 and move it out in the front. So 2 times log base 4 of 6. And I know that log base 4 of 6 is approximately 1.2925. So if I multiply that by 2, I'm going to get 2.585, and that is an approximate solution of the log base 36. Again, if you want, you plug this into your calculator. 4 to the 2.585 exponent should get you close to 36. So here's an equation that involves logs, and we're going to use multiple properties that we've learned to simplify this and get it to a place where we can solve for the value of x. I'm going to look at this first log, and I see a 3 on the outside. So the power property says I can take that 3 and move it up to the exponent of the x. So I can rewrite that as x cubed. And this is still minus log base 5 of 4. And that equals log base 5 of 16. Well, I'm trying to work towards getting one log on the left, one log on the right, and hopefully they're equal so that I can drop the logs and then just set the values equal. Well, here I notice that log base 5 minus log base 5, when I subtract, the quotient property says I can put those together in one log by dividing. So I could rewrite this as x cubed over 4. Now I have log base 5 on the left, log base 5 on the right, which means the property of equality for logarithms says I can drop the logs and say x to the third over 4 equals 16. And now that I can just solve for x. So x cubed equals 64. You can get rid of a cube by taking the cube root of both sides. And the cube root of 64 is 4, because 4 to the third power is 64. And so x equals 4. Here's another equation with logs, and we're going to use some other properties. I notice that I'm adding the two logs. So the product property says I can do log base 4 of x times x minus 6. So now I have one log, and that equals a number. Now I'm going to use the definition of logarithms, and I'm going to take my base 4 to the second power, and that's supposed to equal x times x minus 6. And that's just the definition of logarithms, taking the base, the exponent, and that's going to equal what's after the word log. And so now I can solve this. I can solve this for x. 16 equals x squared minus 6x. I'm going to bring the 16 over and set it equal to 0. So now I'm looking for two factors of 16 that add to be negative 6. How about x minus 8 and x plus 2? Using the diamond here. So I can see that x is going to equal 8, or x is going to equal negative 2. Now I have to plug those back in to make sure that they work. So I'm going to go up here, and I'm going to take the log base 4 of 8 and plug that in for x. So here you see proof that when I plug in 8, it works, because I end up with log base 4 of 4, which those will wipe each other out, and so you get 2 equals 2. Now we'll try negative 2. When you plug those values in, you get log base 4 of negative 2, which doesn't exist, and log base 4 of negative 8, which doesn't exist. Neither one of those are defined. So we're going to say that negative 2 is an extraneous solution, so my only solution here is x equals 8.